All right, hello everyone. Welcome back to Physical Geology 1403. Today is our Exam 1 review day. Yay! Okay. Today is all about your questions. So before I ask if you have any questions, let me just give you a little bit of what to expect here, okay? For the rest of the class, let's start off with that. After today, we will be entering Module 2. In Module 2, we are learning about surficial processes, mostly the things that happen on the Earth's surface or near the surface, okay, that incorporate the knowledge that you've learned about minerals and rocks thus far, but we're looking at a more holistic viewpoint, okay? So how does changes in Earth's climate affect this? What about glaciers? What about deserts? What about all that stuff, okay? So that's Module 2. It is shorter than Module 1. It's only 4 lectures, okay? So Exam 2 is naturally going to be shorter, but that's getting ahead of ourselves, all right? So that's what we're talking about after today. That'll be the next 4 lectures. Today, your exam, which will open, is all about just Module 1, lectures 1 through 7, okay? So it is going to be 40 questions long, which sounds like a lot, but that covers 4 weeks of material. I think 40 questions for 4 weeks of material is pretty fair. Yep. Okay, I need to test you over 7 different subjects. All right. So when you're taking your exam and you're thinking, Professor Hart, just remember that. Okay, it could be a lot worse. It has the usual stuff: short answer, multiple choice, true, false, ordering, matching. However, there is no mineral or rock identification on that. Yes, yay, yay. Don't worry, that'll come later on your lab exam. No. Yeah? Okay. Is that one of your jokes? No, it's not one of my jokes. I know sometimes it can be hard to tell if I'm telling a joke or not, but no, it's not one of my jokes. I could tell you a joke if you want. You guys want a joke to start off the day? Yeah. Okay, all right. So a frog decides he wants to know his future. So he calls up a fortune teller. And he asks this fortune teller, hey, can you look in your crystal ball and tell me what's in my future? And the fortune teller says, yeah, sure. So she pulls out her crystal ball and she's doing her thing. She's like, oh, there is a beautiful girl in your future. And the frog's like, oh, no way. Where do I meet her? And the fortune teller is just like, oh, she's obsessed with you. She wants to know everything about you. She's so interested in you. Where do I meet her? Tell me where I meet her. Do I meet her at a club or at a party or something? And fortune teller says, no, biology lab. Oh, yikes. What's up? I didn't get it. You didn't get it? Oh, yeah, there it is. Yes, yes, yes. Not exactly the date he had in mind. Huh? I like that implication. Yeah, you like the implication? What implication? Well, no, I'm just kidding. I'm just kidding. I don't know if you've ever seen It's Always Sunny in Philadelphia. Have you ever watched the show It's Always Sunny in Philadelphia? No? Okay. All right, never mind then. Reference you wouldn't get. All right. Where was I before I got deviated by the request for a joke? Another one? Okay, we have to get to the review at some point, people. One more? All right, 2 astronomers spent 24 hours staring at the moon, and then they got tired and decided to call it a day. You can't believe how bad these are, can you? I thought you were the dad joke master. Am I not? Are these not good dad jokes? If it's a bad joke, it's a good dad joke. All right? That's kind of base level there. All right? Sure. Okay. We'll go with that. Okay. Are we ready to move on? Yes. If you do want more jokes throughout the course of the day, please ask, but it can't be all a joke-filled day. All right? Huh? Stand-up comedy. That's basically what I do on exam review days. If you guys get bored, just ask me for a joke. All right. Where was I? I told you about that, and I told you about that. Oh, it is timed. OC requires me to have a time limit on my exams. but because I hate taking timed exams, I have maxed out the time limit. 500 minutes is the most time that Blackboard Ultra lets me put on an exam. So you have 500 minutes in one sitting. You cannot save it. You cannot close your computer and come back to it later. If your computer loses connection with the internet, if you refresh the page, if anything happens to this exam while you're taking it, it will auto-submit. Please make sure that you are in a good, solid place, somewhere you can sit there for however long you think you might need, that has a good internet connection. Go to the LRC, go to the library. If you need to take it at home, please do so. If you need to take it at school because you have even crappier internet at home, please stay here and take it. Whatever you need to do to make sure that you are in the best possible situation to take this exam, take those measures. Every now and then, something will happen. My exam 1 opened in fall 2, about the same time that we got that really bad snowfall back in 2021. Everybody lost internet during the window that the exam was open. So I understandably reopened it once internet services came back up. There are a few situations where I will be absolutely understanding. If it is a story that I can confirm, then yes, I may wipe a partial attempt and let you go again. But believe me when I say that Ultra records certain things like your interactions with the exam, how long you've had it open, etc., how long you've spent on each question, etc., etc. So I can tell most of the time if your story checks out. And if it doesn't check out, I will not offer you another attempt. So please do yourself a favor and put yourself in the best situation prior to something happening. Okay? 500 minutes, 40 questions. That's about 12 minutes per question. But remember, some of these are going to be real easy. True, false questions probably aren't going to take you 12 minutes to answer. Some of the short answer questions you might want a little more time on. And this is where I give you my first piece of exam taking advice. I recommend not just starting with question 1 and going all the way down to question 40. I recommend kind of just perusing through the whole exam and seeing, okay, well, I've got this many short answer questions, this many short format questions. These ones won't take me long. Maybe do the ones that won't take you long first. The ones that you're more confident about, do those first. And leave yourself more time on the back end for taking care of the longer format questions. It'll give you that much more confidence. Because if you spend an hour trying to figure out, going through your notes, pouring it over, and agonizing over how to answer the first short answer question, right? And then you realize there are 6 more. Well, you don't have 6 hours left, maybe, in the time that you have available to take the exam. Huh? So make sure you give yourself plenty of time to do as much of the exam as you possibly can. That's my point. All right? Other than that, I'm not going to tell you how to take an exam, really. If you want to ask for advice about a particular thing, I can give you strategies that I've learned. But for the most part, I treat you all as adults and assume that you know how to take exams at this point. Sound good? Okay. Well then, I think that's probably all I've got. Oh, well, aside from the fact that once this exam review is over and I have posted it for all my classes, the exam will open. And you will have a certain period of time from that moment to take the exam. I believe I have it closing on the 15th. Okay, so you've got the weekend, basically, right? Because 13th, 14th, 15th. Yeah, Sunday night, you've got until Sunday night because Monday is when I want to start grading them. All right? For those of you watching this later in the future, ignore those dates. I'll let you know what dates are relevant to you. Okay. Any questions about what we've discussed so far? The format, the layout. Any of that? Yes?
Can we do corrections?
No. Exams do not have corrections. They are the only thing that I do in my class that I don't let you do corrections on. Labs, discussions, as many times as you want. Those are learning experiences. Those are formative. Exams are summative experiences. That's for me to evaluate what you've picked up so far. And if you do perform poorly on this one, then that gives me a little bit of information on who I maybe need to focus a little bit more on so that they perform better on the next one. Okay? Good question. Anything else?
that we've taken for it?
Lectures 1 through 7 all have the potential to be on here. I'm not saying that they are all equally represented, but they all have the potential to be on this exam.
Is there any specific one we should like focus on?
I would say you should probably focus on lecture 1, 2, 3, 4, 5, 6, and 7.
Wow.
You're welcome. You're welcome.
Are the questions any similar to the questions that were provided on the lab?
That's a good question. All right. So the question was, are the questions on the exam in the same format or, you know, in the same style, I guess you were asking, as the ones on the labs? And yes, a lot of them are. They reference particular things that we learned in class. Okay. It wouldn't be exactly fair of me to test you on something that we spent 10 seconds on, right? So we're learning about the things that are of the most value, and of the things that are the most value are the things that I often spent the most time on. Okay? Things that you should definitely recognize from our discussions. What else?
Will there be like unexpected things that we haven't fully delved into?
No, there's nothing on the exam that I won't have taught you. There may be some things on there that you perhaps didn't think were as important, and that's where today comes in, right? This is why I really encourage you to look at your notes and think to yourself, okay, I have a whole paragraph about this subject, but one sentence about this other one. Maybe I should ask for a little bit of elaboration on that one, because if that sentence worth of information, if that topic is on the exam, I don't really have much to work with. You know, that's what today is all about.
Will there come like the different types of texture?
Properties of rocks and minerals may be on here. There is no identification, but I may reference the properties of rocks and minerals because they are relevant to what we learned in lecture, right?
So things like if it reacts to acid, like things like taste, all that.
Yeah, exactly. Things like reaction to acid, igneous textures, right? Those directly relate to the manner in which that rock or mineral formed. And that's what we discussed in class. Lab is all about the using of properties for identification. Lecture, we use those properties for interpretation. And that is definitely something that could be on the exam.
I wonder if it'd be possible, given that you've all the lectures are recorded, that someone would be able to use AI to get everything you've ever said.
Ooh, like pass all my lectures through an AI machine. I'm pretty sure the only AIs that are that sophisticated that can generate notes for you from my lectures, I'm pretty sure those are paid subscription services. I don't think there's a free AI software out there that is that sophisticated.
But there is AI.
There is, yes. There is AI that will do
if
that.
You were,
Conceivably, if you're willing to pay enough money, it would be pretty easy to cheat through my class. But why would you pay money to do something that just takes a little bit of effort? That's my philosophy anyway.
Wow, you do talk about a lot of things.
Huh?
You do talk about it.
I do talk a lot about a lot of things. That's because I have 8 weeks to teach you a traditionally 16-week class.
Makes sense.
Yeah.
Did the review started already?
Has the review started already? Yes. We are 14 minutes into our review. From the moment that I say, hello, everyone, and welcome back to Physical Geology 1403, that is when it begins, our lecture, every time.
Can you explain more about you remember the bearings and the 90-degree angles?
Okay, so this is our first content-related question. Is everyone ready to move on to the content part of the review? Do we feel good about the format, the layout, what to expect from the exam?
Can we go back to the format if we need to?
Yes, absolutely. You can anytime. Okay. I just want to make sure that everyone's ready to move on. No, absolutely no backtracking allowed. Only forward. Okay. No one? All right. Repeat your question.
When the bearing and the 90-degree angle, like, don't really, make sense in my head.
Well, it didn't make much sense in my head either. Say it again. Let me try and understand what you're saying.
Okay, like if you can explain a little bit more of like, you remember the rock we saw with the bedding?
In which lecture are you talking about?
Just the last
The last one
In metamorphism.
with the pressures, the express pressure, I think.
No, last time we talked about metamorphism. Are you talking about
Are you talking about the rocks that have the lines in
Yeah, something like that.
it?
the rocks that had the what? Sorry.
The rock that you showed us that was like at an angle and it had the lines in it.
Oh, with the foliation.
Yeah, yeah,
Okay, what about that? You want to know? You want me to go over that again?
yeah, yeah.
Sure. Let me pull out my pens. On review days, I exercise my art skills, such as they are. We're all tight. You guys won't judge me too much, right? All right. Foliation. So I shall paint you a picture. Here we have some layers of shale. Okay. If that shale gets buried deep enough, experiences enough heat, it will metamorphose. Without directional stress, it will turn into hornfels, just baked mudstone. With directional stress, something's going to happen. My beds may warp like this. How many do I have up here? 4? Okay. I may get something like that. Okay. Folding, we call that. Remember, that's happening on the large scale. That's happening to my bed. Foliation is what happens to the individual minerals. In this case, my shale being full of clays, those clays are going to reorient in what direction relative to the stress applied? Perpendicular. Bingo. Okay. So if my stress, let's use red to designate stress, huh? That makes sense. All right. Red is the direction of stress applied. In what direction are my minerals going to be oriented? Vertically in this case, right? So all my clays are going to be doing this. So while my beds of rock are going to be doing this funky dance of folding, all my clays have reoriented in that direction, which means that if I were to take a hammer and slam it on that rock, because of the direction all my minerals are now oriented, in what direction is it going to split? Is it going to split along these bedding planes?
No.
No, it will split in the direction that all my minerals are oriented. I'm going to make sheets of rock split off like that. Like, well, that was that piece of diorite. That the gneiss came from that, not slate, but same concept. Okay, slate is just a good example, an easy example to understand with shale as my originating rock. Okay, but the concept is the same for all foliation. For my students who can't see that very well, let me zoom in here. Okay, and maybe step out of the way here, so you can see my undulating beds here, my folded beds, stress coming in from these directions. And now all my minerals have oriented this way, and so my rock will break apart vertically because of the foliation inside of my rock now. Okay. That answer your question? Does that make a little more sense?
Yeah.
Perfect. All right, hit me. What's next?
Can we go over the cleavages of the rocks? Or like,
Minerals?
yeah.
Mineral cleavage? Absolutely. Anyone remember the definition of cleavage that I gave?
Like how many directions it breaks into, right?
Yes. Okay, so minerals will break in one or more directions based upon what?
Based on the formation.
Formation. Let's explore for another word here.
How it's made?
Huh?
How it's made?
How it's made, go into more of that. Elaborate. How it is made, by what, and how. No, that has to do with weathering. Huh?
pencils how it's crystallized?
How it's crystallized, you're still saying about the same thing.
Atomic structure.
What about its atomic structure?
I guess. All right.
Okay, well, let's work with that. Something about its atomic structure is making a mineral break along one or more, or yes, none. There can be no cleavage, but if it has cleavage, one or more particular planes, right? What could be making that happen? Remember that a mineral is nothing more than solid chemistry. You've got bonds, atoms that have bonded together, okay, and made a solid, a crystalline solid. That means that your mineral is nothing more than a repeating pattern of the same arrangement of atoms in a bond. So if I have 3 different bonds in my molecular chain, and one of them is weaker than the other 2, and I exert stress on that bond or on the entire whole of this chain, which bond is going to break first? The weakest bond. And since a mineral is nothing but a repeating pattern of that same bond, guess what? That mineral is going to break along the planes of those weaker bonds all the way through its structure. That's cleavage. Cleavage is the manner in which a mineral breaks based upon its internal atomic structure. Okay?
Also, right.
Huh?
Saying you're only strong as
You're only as strong as your weakest bonds? Huh? Right? Well, I think most people use that to justify leaving behind members of a tribe or a group, but I guess that applies in the natural world.
I was just thinking of the same. Okay,
You're not trying to deliver a social commentary? No, okay. Okay. Now, why would there be more than one plane? What does that represent?
Different type of weaker atom.
There's more than one weak bond in that chain.
Yeah, you have those ones to represent that.
Yeah, I do. I've got these little blocks, okay? So if it's breaking in 3 directions, then there are 3 planes in my molecular chain along which those bonds will break first when stress is applied, right? And then we describe the angles. The angles don't mean anything to you and me other than a way of identifying, okay? Think of the properties of a mineral as the fingerprints. We are fingerprinting a suspect, okay? In the same way that if one of you ended up murdered today, all of us would get fingerprinted as part of our booking process to figure out who did it. We are fingerprinting each one of these minerals to figure out who done it. Which one are you? Let's look at your fingerprints. Yes. No one go burn off your fingertips now, okay? All right. You've watched too much Bones. You ever watch Bones?
I watched like different crime things, but I watched Bones.
If you like crime shows, you need to watch Bones. It's so good. It's like 12 seasons. Yeah. Season 5? Oh, I watched it all the way through. So good. Yes.
Can you elaborate more on fossil succession?
Fossil succession. Okay. I brought up the Bones TV show, and now we're talking about fossils. That's appropriate. Okay. Fossil succession. We use fossil succession as a way to identify, differentiate bodies of rocks from each other vertically through time and also across distance. Okay? So how do we do it through time? Well, let's say I have a species of shellfish, like a clam, that only appears in the fossil record for 1 million years. I may slice that 1 million year layer of rock, that layer of rock that represents that 1 million year period where that clam is present and only present in that 1 million year period of time. I may call that a particular layer of rock. because that clam is only present there. However, in the layers above it, I can see that there is a species of clam that obviously evolved from the former one. It's different enough that I call it a separate species, but the succession is obvious. So vertically, we are observing the succession of one organism after another through the fossil record, and that helps us kind of differentiate and specify periods of time and layers of rock from each other through a vertical sequence of rock. Now, how does this work over horizontal distance? Well, let's say that, let's go back to my original example of that clam that only lived for 1 million years, okay? We only have fossils in that one layer of rock. Well, let's say that I go 100 miles that way, and now my sandstone with clams has become limestone with clams. Am I in a different period of time? No. Why? Because the clam is still there, and that clam only lived for 1 million years. I may be in a totally different layer of rock, or type of rock, I should say, but the time between these two totally different rocks is the same. They were both deposited at the same time. Why? Because that clam only lived for 1 million years, and it is present in both. Okay, so this is how fossil succession can kind of, using fossils, can help us correlate rocks across vertical and horizontal time. Okay, does that make sense?
Does that mean that the depth of the I guess these particular fossils that has to be like no, not that great, right? Because if you have well, I understand the whole concept of having two different types of rocks and minerals on that layer, but if you have the same fossil but on different layers, then there has to be some sort of like distance cap between the layers, right? But that's not
really a distance cap. What I think you're aiming at is that the environments must have been substantially different. Is that what you're trying to express here?
Yeah.
And you're correct.
So like areas that used to be an ocean, or that used to be not be covered in ocean.
Now you're thinking like a geologist interpreting rock. Okay, so if I found this fossil in a layer of sandstone, I might interpret that as a beach or a near shore environment. You know, you walk out from the beach, and for at least a couple 100 feet past the beach, there's still sand. Put your face under the water, there's still sand under you, a lot of sand. Clams could live in that, right? So we may be looking at a beach or near shore environment. Go 100 miles further away, and all of a sudden your fossil is in limestone. I'm in the deep ocean now. I could interpret that as a deep ocean deposit. But the clam is still there. This clam obviously could live in both shallow and deep water. I am now interpreting the past tectonic and geographical changes, the changes that have happened between when that clam was alive and now. If I'm in the middle of Utah or Montana and I'm looking at a beach deposit with this clam, I'm thinking to myself, there's no beach around here. That's because whenever this clam was alive, there was a beach. And 100 miles further away, if it's in limestone, guess what? That used to be the deepest part of the ocean. Okay? Or a deep ocean.
That clam is still there.
The clam's still there. So it's still, the beach and that deep deposit of limestone were deposited at the same time, just at different depths of water, just like you were saying. This one way out here, deep underwater, and this one over here, near the shore.
So they don't necessarily need to be on the same layer to be part of the same time period. Is that what you're saying? Because if they're
they will be approximately. So not all layers are exactly horizontal, right?
Well, yeah.
They are all deposited horizontally,
right,
contemporaneously, but you know, this happens over time. Doesn't even need metamorphism. Simple tectonics can cause sedimentary layers to get tilted. I've seen sedimentary layers that were tilted so much that they actually overturned, and now our law of superposition is all messed up. Law of superposition is what? Oldest on bottom, newest on top, right? But they've been tilted by tectonics so much that newest is on bottom and oldest is on top. And you're like, wait, what?
So it's not
really messes you up.
Relative to depth, per se.
The type of rock is, and this is something that we learned in sedimentary rocks, but we will discuss more of later on. Something like sand, very common near continents. This was actually a question on your lab. You guys remember why? Why is sand so common on or near continents?
Because he's broken down igneous rock,
Igneous rock containing what?
silica,
Which is the mineral?
that makes it like
What mineral is pretty much all silica?
feldspar.
Quartz. Good. Quartz, present in felsic igneous rock. What's the general composition of continental crust? Felsic, right? And so we get a lot of quartz on continental igneous rock. That quartz breaks down, but not as fast as everything else because it is very difficult to break down. It's more stable under lower pressures and temperatures because it's one of the last minerals to form in the magma, right? And it's very hard. And so our sand, mostly quartz, ends up being deposited near our coastlines. Why isn't there a bunch in the deep ocean? Because the ocean crust is mafic. No quartz in that.
Basalt.
It's basalt or gabbro. No quartz. Too extraordinarily little quartz. Only rarely do we find quartz and stuff like that. Not enough to even consider as being real in our class today. Okay?
Interesting.
So, I can make an interpretation of where I was relative to the shoreline based on the type of rock. So if I'm looking at this deposit where this clam is alive and it's quartz sandstone, I know I'm near the shore. If I see this deposit and it's limestone, I know I'm far from shore, probably in a warm, shallow ocean. And if I find it in shale, I know I'm really far from shore because those are very fine grained sediments. It would have to be very low amounts of energy for that to be deposited. We'll talk about these interpretations later on when we discuss shorelines. Yeah.
Well, can you talk about the difference between clastic and non-clastic sedimentary rocks?
The difference between clastic and non-clastic sedimentary rocks. Before I answer that, can anyone else answer that?
Plastic is I remember from memory.
Okay. Memory is fine, but I really would encourage you to put it in your notes. You can hold a lot more in your notes than you can reliably call on from your memory. Yes, Emily.
Plastic, solid, weathered products, and non-plastic is chemically dissolved weathering products.
Good. All right. So clastic is made from the solid, mechanically weathered products. Okay. You mechanically weather something, big rock becomes small rocks, right? Easy. And those small rocks go on to make a clastic sedimentary rock. On the other hand, chemical weathering dissolves stuff. So you get a whole bunch of dissolved ions in your water. Those ions later go on to precipitate out and make a non-clastic rock, or those ions are incorporated into the shells and skeletons of little wee beasties in the water, which then live their lives and die and then fall to the bottom of the ocean and then get incorporated and become another type of non-clastic sedimentary rock. Okay?
Interesting.
Is plastic or non-plastic, is that organic?
Organic is a type of non-clastic sedimentary rock, yes.
So it's just the kind of the method of development is that classifies clastic and non.
The materials dictate whether it is clastic or non-clastic.
Like the type of minerals in the rock? Or?
No, am I working with solid pieces or am I working with what at one point was something that was alive or something that was dissolved?
That's why non-plastic.
Think of
rocks.
sand. Think of sandstone, made out of sand, right?
Right.
Mechanically weathered, broken down pieces of minerals. Nothing that's dissolved is in that, except maybe what made the cement that's binding it all together. Cement is often from dissolved stuff as well, okay? But most of your substance in your sandstone is going to be from mechanical weathering, as opposed to, say, micrite limestone, okay? Sure, some sand or shale may have gotten stuck in there because it was washed around by the water. Maybe a storm brought some in. However, most of that is going to be calcite crystals that precipitated out of whatever was dissolved in the water. No solid particles were involved in making that calcite, which made that micrite.
And that's why non-clastic rocks tend to be organic a lot, right? Just because
They don't tend to be organic a lot. Organic falls under the non-clastic category. Organic rocks are non-clastic, not the other way around. Not all non-clastic rocks are organic, but all organic rocks are non-clastic. Okay? Yes?
Is there like an easy way to tell the difference between sedimentary, igneous, and metamorphic rock?
An easy way to tell the difference between them? Well, their properties, right? For one thing, yeah. But just looking at them, it's like a quick and dirty, that's an igneous rock or that's a sedimentary rock. Like you walk into your friend's house and you walk over to their table and they've got a rock sitting there and you just want to impress the heck out of them. Oh, look at this igneous rock. And they're like, wait, what? And you're like, oh, I took geology. I should tell you about Professor Hart. This guy, what's so cool, right? No. So I guess if I really had to throw it in a nutshell, igneous rocks are usually, you can tell them by the fact that they're a bunch of interlocking crystals. Okay? That's not always 100% going to take you in the right direction because non-foliated metamorphic rocks are also interlocking crystals. So there is an exception, but all igneous rocks are going to be interlocking like that. Like they grew out of the magma and interlocked with each other, right? For sedimentary rocks, this can be difficult. Most of the ones that you will see are either going to be classic sedimentary rocks like shales, sandstones, conglomerates, things like that. And those are going to be just kind of like bonded. Okay, they'll still have that grainy feel. A lot of sandstones will look like sand still, right? It's just it's made of rock. Okay, so if it looks like it's made out of grains, you're probably looking at a classic sedimentary rock. Non-classic sedimentary rocks can be a little bit trickier because they are commonly made from microscopic crystals, unless it's made out of fossils. If it has fossils in it, if it is a non-classic sedimentary rock with fossils in it, you're probably safe assuming that it is limestone. Bless you. And then as far as metamorphic rocks are concerned, the only really easy way to tell them apart is if they are foliated. If someone's trying to sell you a granite countertop and your minerals are in a parallel alignment with each other, what are you looking at? Whatever this rock is, it's been foliated. So it ain't granite, right? You're probably looking at a gneiss, okay? Which they often do try to market as granite, okay? Gneiss is, well, it's nice. I mean, it's still good for building material, but it's not granite. So if granite's what you want, you don't want something that's got those foliated minerals, okay?
So you said igneous rocks are
Interlocking crystals.
There you go.
Yeah. And like I said, that's not a 100% foolproof way of telling them apart from, say, non-foliated metamorphic rocks. But if all you have is 5 seconds, those are just a few general broad ways that you can try and tell them apart. If you ever go on Jeopardy and you have 5 seconds to tell a rock, right? Just those are some rules that could send you in the right direction.
On Jeopardy.
Yeah. All right, what else?
So you said we're not gonna like identify particular rocks or minerals, but will there be questions that are about how to identify particular rocks or minerals? For example, like characteristics or properties.
Yeah, that has the potential to be on there. Things about properties of minerals are still relevant to their interpretation. I will not ask you to identify anything on this exam, but I will reserve the right to reference those properties and how we identify, or not identify, how we interpret things about minerals and rocks using them. Because it's in lecture that we learned what those properties mean.
Right.
Igneous rocks are phaneritic or aphanitic or whatever other texture for a reason, and we discussed that in our class. And those reasons help us interpret things about Earth's past. Lab uses those properties so we can tell the rocks apart from each other. I'm not exploring or testing you on that aspect, but I do reserve the right to test you on the interpretive stuff that we learned in lecture.
Gotcha.
Definitely do not like how the different coals form again, because I kind of remember that.
Coal. Yes, sure thing. First off, you need an environment where the vegetation does not decay away. So an anoxic, shallow water tends to work best for this, which is why swamps tend to make the most coals. Okay, so you get some shallow water, it's anoxic, that means there isn't enough oxygen to cause soft tissues to decay, at least not very quickly. And so all these soft tissues from these plants get buried deeper and deeper and deeper and deeper. And as that happens, they start getting a little bit cooked. That means they start getting a little heated, okay, from the depth of being buried. A little at first, and the deeper they get buried, more and more, right? The first step that you have, peat, P-E-A-T, peat. Peat is essentially just squished vegetation, right? It breaks apart really easy. You can burn it. It would stink like heck, okay? But you can burn it. You can get some fire off of that sucker. Then you bury it more and you cook it a little more. You get lignite, which you can still see some remnants of plants in, but for the most part, it's hard like a rock. That burns more efficiently. Not fantastic, but far more efficiently than peat. Imagine if you took 3 feet of peat, you could compress it into about a foot of lignite. Then you cook that and pressurize it even more. You take a couple feet of lignite, you compress that into bituminous coal. That is what we typically look for and burn in our coal power plants. A coal mine typically targets bituminous coal. Okay. Some trains use that. Steam trains often use that. It's the coal Santa puts in your stocking, all that. Okay. And then if you bury it even more to the point where it reaches metamorphic conditions, we have a new name for it. It is anthracite. It's still coal, but it is now a metamorphic rock. Yes?
So the last stage of coal is metamorphosized?
Yes. The last stage in coal requires metamorphism and it becomes anthracite. So the sedimentary or the organic sedimentary versions, peat, lignite, bituminous coal. And then after it passes that pressure and temperature threshold where diagenesis ends and metamorphism begins, that's when it becomes anthracite.
Can you explain the magmatic evolution?
Magmatic evolution. So Bowen's reaction series is what you're referring to, right? Okay. Bowen's reaction series is the sequence of changes that occur in a magma as different minerals are forming. So for example, we know that olivine forms at about 1200 degrees Celsius. Well, if my magma cools from 1201 degrees Celsius to 1200 degrees Celsius, I start forming little olivine crystals in it. As those olivines grow and get bigger and bigger, they're making copies of their internal atomic structure on top as they get bigger, right? Larger and larger crystals as time goes on. They are taking irons and magnesiums out of my ultramafic magma from the mantle. Eventually, once enough olivines form, I will have gone from an ultramafic magma to simply a mafic magma. Why? because the ratio of irons and magnesiums that are left in the magma, that ratio of iron magnesium to everything else, is lessened. So I've gone from an ultramafic composition to a mafic one because the irons and magnesiums relative to everything else have become more normalized. They are approaching equal quantities. They are not there yet. They're approaching it. So I can't call ultramafic anymore. Ultramafic, mafic. Time goes on, I'm growing pyroxenes, calcium plagioclase, biotites, hornblende amphiboles, things that take out more irons and magnesiums. And gradually, as time goes on, my magma chamber is cooling as each one of the crystallization points for these minerals is passed. Okay. Eventually, I reach a point where I cannot call it a mafic magma anymore. It is now intermediate. I have approximately equal quantities of dark and light silicate making elements. Okay. I now have an intermediate magma. Time goes on even more. I can grow my potassium plagioclase. I can grow my muscovite micas. I can grow all of these different things. Okay, light silicates more than dark silicates now. And we have entered the felsic zone. Okay, so few irons and magnesiums left, but still plenty of the light silicate stuff, the sodiums, the potassiums, the calciums, the silicons, the oxygens. Okay. And then finally, right there at my magma chamber's dying phase, it's got not much left in it. That's when all of your rarer elements, the things that don't easily bond with the other things that came before, that's where those get incorporated into the minerals. Okay? So the rare stuff like lithium, gold, silver, all those things are formed right there at the end.
The dark minerals are formed first.
First. Dark silicates form at higher temperatures, and therefore they form first.
Because like they're more dense.
They do tend to be more dense, yeah. Iron and magnesium rich minerals, those dark silicates are more dense. Yes. That's Bowen's reaction series. The sequence of minerals that appear as a magma chamber is cooling off. And as they are growing, they change the ratio of elements in your magma chamber.
What if the like minerals like clump up again? Because I don't. Because you know how certain things like I guess coalesce to one another.
Like grow together?
Yeah.
Why do they do that? Well, what happens if I'm growing quartz, sodium sodium feldspar or potassium feldspar and amphibole at the same time, and biotite or muscovite? What happens if they're all growing at the same time? Where do they grow? They're just growing wherever they started in that magma. And therefore, if they run into another crystal, they have to go around and with that crystal. And so the reason why all of these igneous rocks are a bunch of interlocking crystals is because eventually they ran out of room to grow on their own, and they started growing in and around and all through these other minerals as that magma was cooling off.
I know we talk about like, the coals, but what about like oils, natural gases? I don't really remember that right now.
Oils and natural gases form as part of remember what I said about coal, how coal forms. You get a bunch of organic material, you bury it, and eventually it turns into this energy-rich rock. Let me explain why that happens. This is going to be a rare moment where I sit down. It doesn't happen often. But for this topic, I just feel like we need to chill for a second. All right. Someone talk to me about what trees do. Okay, so they go through a process where they crack, they absorb carbon dioxide, they crack the carbon off, they release the O2, and they use the carbon to build their structures. Sure, that's how they build their physical structures. Through what process do they do that? Huh? Say it louder.
Photosynthesis.
Photosynthesis. Okay. Using what energy source? The sun. Okay. These trees and other plants use energy from the sun to power a process in which they effectively store energy in the bonds they make in their structures using oxygen, hydrogen, and carbons. Trees and all other plants basically are converting light energy into solid potential energy. That's why wood burns. That's why coal burns. Coal is a great source of energy because it's just compressed. If you think of each tree as a battery of potential energy, coal is like if you took a battery this big and you condensed it into a double A, but you still had the same amount of energy, right? Like if a car battery, if you could somehow put the same amount of energy from your car battery into a double A, that's powerful. Think of coal like that. So that's how coal works. You and I and every other living animal organism work very similar. We store energy as well. Plants store energy. Algae stores energy. Phytoplankton, zooplankton, they all store energy. And so when a whole bunch of tiny little critters in the ocean or algae die and fall to the bottom of the ocean and get incorporated into the sediment there, this typically happens most often in the ocean. Okay, they get incorporated into the fine-grained sediments there. They get buried. They're in an anoxic situation, right? No decay. The hydrocarbon bonds in their bodies that have effectively acted as batteries go through a similar process like coal did, except instead of turning into a solid, it turns into a liquid, petroleum, a hydrocarbon liquid, okay? And so that's where the petroleum comes from, okay? Is through this process of getting cooked, just like the coal, but it turns into a liquid instead of a solid. Now, as time goes on, it migrates through the rock. Usually it will leave its host rock, wherever it was formed, usually in shales, black shales, deep under the ground, okay? It will migrate out of there, trying to seek zones of less pressure. It will try and make its way up closer to the surface, flowing through rock that is very porous. Well, what rock do we know of? What sandstone rock do we know of is very porous? Sandstone is very porous, right? I said what sedimentary rock is what I should have said. Sandstone, okay? It's very porous rock. And that's why most often we will find oil reservoirs in sandstone. It's what we call a conventional reservoir. You've probably heard this term before, right? Conventional oil plays are ones that are easy to find in porous sandstone. More and more often, those are becoming more difficult to find because we have found a lot of them, which is when something like an unconventional reservoir comes in. And unconventional, that's when we have to do things that are a little more complicated to get it out, right? Can anyone name a process, an unconventional process, by which we need to remove oil from typically non-porous rock? Fracking. That's what fracking is. You basically drill a hole underground into the layer that you want to get the oil out of. It's usually a source rock that the oil never left because there was nowhere to go. Okay. And you drill sideways you do a lateral well into that formation, and then you pull your drill up, and then you just pump it full of water. The frac fluid they put in down there is 98% water. There's a few other things in there. It's mostly just try and thicken up the water a little bit to make it more effective when you pressurize it. But after you put enough water in there, you really crank down the pressure on that. And the reason why is because you're trying to use that water to crack the rock. That rock does not naturally have pore space that the oil can flow through and therefore out of. So you need to crack it. And you crank that pressure up and you crack that rock and you crack that rock and you crack that rock. And then you push a whole bunch of sand down there. We call that proppant. It's meant to hold those cracks open so that when you release the pressure and pull the water out so that the oil can come out next, those cracks are held open by that sand. And that's what a fracking well does. It cracks the rock and allows the oil to come out after you've pulled out your water.
Interesting.
Yeah, any questions about that? Fracking is a big concern, not only in our area, but all over the world, really. I was living in Ohio when Youngstown, Ohio had an earthquake. Youngstown never has earthquakes. Ohio is not known for its earthquakes. But an earthquake in Youngstown, Ohio made everyone freak out. And fracking ended up being what everyone blamed it on. Now, at that point in time, there was not sufficient evidence to suggest that earthquakes could be caused by fracking operations. It was just a convenient scapegoat. And so that's what raised this whole issue, this whole problem. However, in the decades since then, a lot more data has been collected by oil companies and by environmental companies. And yeah, at this point, we know fracking does, in fact, induce seismicity. It can, in the right situations. I'm not saying that all earthquakes are caused by that, not by a long shot. But what would happen if, say, a little bit of fracking fluid made its way into a fault line? Remember, a fault is essentially a crack in the ground along which stress builds until it slips and an earthquake results. We'll talk more about that in an upcoming lecture. But what would happen if some fracking fluid, some water, made its way into that? It would effectively act as a lubricant, make it slip just a little bit earlier. So, yes,
it's pressurized water in order to break open the
Mhm.
rock. So,
So
would it
if
still
there's-
be under subject to high pressure.
Yeah.
Entering the fault line.
Yeah, and normally you can tell if you're losing frac fluid because your pressure, you can't keep the pressure up in your hole, in your borehole. So if you can't keep the pressure up, you know that water's escaping somewhere, you shut that sucker down because they're afraid of where it might be going. Okay, we've learned since then. That's what they're supposed to do anyway. And so yes, fracking does in fact cause earthquakes on occasion. Matter of fact, I just I can't I can tell you guys, can't like go to the news about it, so don't go to CBS 7 with this or anything. I just made a partnership with the Lawrence Livermore National Laboratory. They called me up and they want me to share information about the earthquakes that we've been having around here. They're going to give me a whole bunch of data sets. They have spent a couple of years collecting earthquake information around here, and they're going to give it to me so that I can have a series of public seminars where I tell people exactly how fracking and earthquakes are related in the Permian Basin. So that's a 2-year partnership that starts in January.
You didn't mention that.
Yep, it's pretty cool. Okay.
So it breaks the sandstone from the inside out.
What does? Sorry.
The fracking.
We don't typically need to frack sandstone. Sandstone naturally has a bunch of pores in it. Normally, what you will frack are layers of shale, which are non-porous and act as source rock most of the time. So a lot of the easy stuff has already been tapped into, the sandstones that contain oil. And if new ones are found, oh my goodness, the oil companies love that. It's a lot easier to drill just one vertical well or a series of vertical wells into sandstone and let the pressure bring the oil up than it is to frack a layer of shale. But because less and less often we are finding those convenient layers of sandstone, that's where fracking is becoming more and more of a necessity to keep up with demand. Yeah. It's kind of like, I always use cookies as an example. You guys realize that? Like, my mind is telling me something. I crave cookies all the time, I'm thinking, and I just don't realize it. It's like making cookies yourself. It's like making cookies in your kitchen instead of going to a store and buying cookies. It's more convenient to go to the store and buy cookies, right? Less convenient, more work to make the cookies yourself. You still end up with the same results. Fracking is making the cookies yourself. You're going straight to the source. You're doing it in your kitchen. The sandstone, where the cookies have ended up, think of that as like the store. Easier to get it out of. All it takes is a little bit of money. Making it in your kitchen, that takes more time and effort. Think of it like that.
But it's not necessarily higher quality petroleum.
Not necessarily, no.
like it would be if you were to make a cookie in your house in comparison.
The quality of the petroleum depends upon the other things. How old that reservoir is. The more it's been cooked, the more gas there will be instead of petroleum oil. Okay.
You did mention that, right? How
Yep.
a lot of it just gets wasted.
Yes,
Natural
we burn off trillions of cubic feet of natural gas in the United States alone, which is a crying shame. That's so much potential energy that we could use. I'm going to stand up on a little bit of a soapbox here for a minute. The energy crisis, you probably have heard people talk about the energy crisis, right? A term that was kind of coined in the early 2000s, late 90s. The only reason why there is anything like an energy crisis, why oil or gasoline gets expensive every now and then, right, is because of how regulated production is. We are nowhere near running out of oil. That is not the problem. There is so much oil underground. We could go at our current rate of consumption. We could go at this current rate of consumption for 200 more years before oil is past its peak and we start having a problem. The reason why there is an energy crisis is because they cap the amount that can be produced and the ways it can be produced. They regulate the production without regulating the consumption. Okay? You can only produce so much oil. You can only produce so much of this. But we're not going to tell Toyota to stop making so many cars. We're not going to tell Boeing to stop making so many airplanes. Right? That's the reason why we are in an energy crisis. It's because they are capping the production without capping the consumption as well. Okay? Does that make sense? Cool. I think we talked enough about that. Unless anyone else have questions about this.
Are those real?
Are what real? The skulls? I'm glad you asked. Let me tell you about these skulls. Last year, I realized we had a problem. The entire department, which by the way, I am on paper, I'm part of the biology department, but that's only because they didn't know where else to put me. So I share resources with them. I do my own budget. I do my own paperwork and stuff. Every now and then I need Mr. Jones upstairs, the department chair for biology, to sign something. Otherwise, I'm kind of my own creature here. But we share, when we're talking about evolutionary biology, we all share the same set of hominid skulls. There's only one set. Each one of these is about $400 to try and get. And that's a lot. That would be a lot to try and get an additional set. So last summer, I decided that I would take it upon myself to rectify the situation. And I took 3D scans of all our hominid skulls, and I 3D printed copies. And those copies, I molded and I shaped a little bit after they came out of the printer, smoothed them down, handed them off to the art department, and they spent a couple of months painting them. So this is a 3D printed copy of the one I just showed you, which I made for about $30 of cost instead of buying a whole nother one for $400.
Wow.
Made a couple of those. Here is the original for this. I'll show you this one. And there's the copy. Some of them I scaled up, some of them I scaled down, just depending on, people can have a variety of what to pick. But yeah.
What are these skulls of?
What are the skulls of? These are the hominid series. So the, I guess you could say the progression of hominids into humans, okay? Starting from a couple million years ago to recent. And we have, the complete sets are up in Mr. Jones's office. He keeps them in his office because we don't want to lose them, or we don't want them stolen or broken. The original set were bought by the department, but then I built these extra copies. So we should have 4 of everything instead of 1 of everything now. We can have a set in every classroom instead of 1 that we all have to share. Yeah, that's what's up with those. That's the first group. The art department has the next set that I printed, and they're working on painting those. And I'm gonna probably start printing the next set here in the next couple of weeks. I should have about 8 more skulls
And
besides those.
Also printed.
Yes, these are actually examples of the next set that need to get painted. This is Paranthropus boise. And this is the 3D printed version. I have not sanded it down yet to prepare it for painting, but yeah.
Oh, that's the real one?
This is the original. This isn't real. No, the real one is, I'm pretty sure, in a museum in France. But this is a copy someone made out of plaster.
And it costs $400.
This costs $400 to get another one of, yes. Because there's only one copy, and the people who have the original can charge whatever the heck they want for copies, right? Or I just take our copy and I 3D scan it, and I can make this for about $30 of plastic. It works. Yeah, exactly. I made these in our fab lab downstairs. Yep. Okay. We talk a lot about these, by the way, in 1404. Yeah. So get ready for that. Those of you taking 1404 from me, we talk all about evolution and human evolution and all of that. It's going to be a good time. Oh, you're excited. Don't lie. All right. Huh? Okay, well, that was a fun tangent we had. What else? It is 10:40. We've been going for an hour and 10 minutes. Yeah. Lithification. What about it? Lithification is the name for the process by which sediment becomes sedimentary rock. Okay? So it's that compression and heating and cementation, the squeezing and the condensation of cementation that makes that loose sediment that can take this loose, unconsolidated sand, right, and turn it into a rock. Okay? Lithification goes from this to this. That's what it does. Pressure? Yes. So it needs to be compressed through the pressure. There does need to be some heat involved. And cementation, because without cement, these grains would never stay together. Matter of fact, poorly cemented rocks fall apart. Okay?
The cement will be like water?
No, cement is the things that are in the water. So calcite can be a cement. Iron oxide can be a cement. Silica can be a cement. Okay? Those ions in the water that may have eventually gone on to become some form of non-clastic sedimentary rock instead hold these grains together as a cement.
Wait, how does like the different materials in the water become cement?
As you are pressurizing your sediment, you're squeezing out air and water. And as the water leaves, it leaves behind a little film of whatever was in that water, whatever was dissolved in there, be that calcite or iron or whatever. Okay? That little film, when it solidifies, kind of sticks grains together. Okay? Think of it as like the glue. The cement is the glue left behind by the water, holding these grains into the shape of this rock.
Man, I'm hungry.
Me too. Shouldn't have brought up cookies. I'm going to take a minute here, and I'm just going to address some of the questions that the online class asked. Where does sediment come from? Good question. Sediment is the product of the mechanical weathering of rocks. Okay? What I call sediment is the product of mechanical weathering. That's where it comes from. Okay? So remember the rocks breaking into smaller rocks. Those smaller rocks, sediment. Okay. Let's see, who else asked questions?
How many people you see in your online class?
How many people in my online class? I have 30 in one section and 16 in the other, in addition to the 13 of you. So I've got about 60 students right now, which explains why sometimes it takes me a while to get to your assignments, because I've got 60 of them to grade. I've got 60 lab 1s, 60 lab 2s, 60 lab 3s. So if I'm a little bit behind, that's why. Today I plan on getting, like I did a whole bunch of the labs yesterday. Okay, any lab that had been turned in yesterday should be done. Today I'm getting to discussion boards and all of that. So.
That means they've all heard you, Angel.
Hmm?
That means they've all heard of you. All those other 45.
Yes, every word that Angel has ever said has been recorded for posterity.
No, well, I still say cool stuff.
You say cool stuff? Okay.
We were talking about stealing like stone from presidents' houses.
Yes, taking a hammer and breaking it off of the president's house. That is something that you said. This video may come up in your trial.
They've heard nothing.
I mean, I have a microphone out there specifically to catch the things y'all say.
Y'all signed the NDA when y'all signed up for that site.
Yeah, sure.
Yeah.
NDAs. All right, so a few more questions from the online class. What properties that you learned in class help you tell the difference between a limestone and basalt? Okay, so they're asking specifically questions from the lab. That's okay. We can talk about that. What properties that you learned in class help you tell the difference between a limestone and a basalt? What do y'all think? I know you were stretching, but now I'm asking you. What do you think? Difference between limestone and basalt? Tell me something about limestone. Anything. Okay. What tests did you do on limestone or on a sample to see if it was limestone? Okay, so hardness. What hardness did you find out for limestone? Is it softer or harder than glass? Think it was harder? It shouldn't have been, but. Okay. What else about limestone?
It's sedimentary rock.
It is a sedimentary rock, true. Can anyone tell me something about limestone?
Silicates.
There's no silicates in limestone. Limestone is entirely non-silicates. Matter of fact, several people in the lab said that with the difference between limestone and basalt is that limestone has less silica. It has no silica. There's no silica whatsoever in limestone. Okay? It is not a silicate mineral.
No plastic calcite.
Okay, limestone is made out of calcite. Calcite is soft. Does calcite react to acid?
Yes.
Perfect. It has a very strong reaction to acid. Therefore, will limestone have a reaction to acid? Yes, limestone has a very strong reaction to acid. Will basalt have a strong reaction to acid? No, there's no calcite in basalt. And guess what? That one probably will scratch glass too. So there are a couple of ways that you can tell the difference between limestone and basalt. Limestone, acid reaction. Basalt, no acid reaction. Limestone, made out of dark silicates. Or excuse me, basalt made out of dark silicates. Limestone, no dark silicates, no silicates at all. Basalt can be pretty dark colored, but it is not made out of silicates. Also, limestone can have fossils. Basalt cannot have fossils. There are lots of ways you can tell the difference between them. Okay. Oh, by the way, another thing that I noticed on the lab, on lab 2, when I was given that lecture about lab 2, and I was telling y'all about properties of igneous rocks, did I not stand here and say that intrusive and extrusive are not compositions? I'm pretty sure I stood here and I was just like, don't do this. We have a recording. We can go back and see if I said that. I recall saying it very emphatically. And yet most people, when I asked about what the composition of continental rock was, said either intrusive or extrusive. Those are not compositions. Felsic, mafic, intermediate, ultramafic. Those are compositions. Intrusive and extrusive are expressions of cooling environment. That's it. Was it underground? Or is it on the surface? That's what intrusive and extrusive mean. That's it. Okay? So if you're wondering why you got that one wrong, now you know. Okay? I really don't know how I can say it better to try and fix this, because even though I specifically say it, there's always people that try and say intrusive and extrusive for compositions. Anyways, coming back to these questions. What does a pure quartz sandstone indicate about the environment the sand was deposited in? Ooh, we already touched on this one today. What do y'all think?
Question was pure quartz sandstone.
Pure quartz sandstone. This guy. Quartz sandstone, nothing but quartz. Camera. Stay with me, camera. Come on, baby. Over here. There we go. Quartz sandstone. What does it indicate about the environment that it was deposited in?
It was about quartz sand. Like the sand was made of quartz.
Yes, the sand that made this quartz sandstone was quartz sand. That is true. Now tell me what that means about the environment.
In a shore.
Maybe near a shore. Why would it mean lots of weathering? What broke down? Well, the quartz hasn't broke down. It's still here. Everything else. Thank you for getting us there. Okay. Everything else but the quartz. Quartz, very stable, doesn't break down nearly as well or as easily. Also very hard, difficult to break down, more difficult than most everything else, right? Therefore, if my sediment is pretty much nothing but quartz, everything else is weathered away, that indicates to me that that environment underwent a lot of weathering. It's true, it could be a beach. There's a lot of weathering at the beach. The waves and the wind and all of that, constantly weathering the materials, right? So it is very possible we could be looking at what is remnants of a beach. Okay, that's one way to interpret it. But what I'm looking for here is that the fact that only the most common, hardest mineral commonly found in igneous rocks is left means that the weathering, there was a lot of it. Okay, that's how we can interpret that. This is an easy one for y'all. How is the orientation of foliation related to stress? Huh? What does it have to do with the direction of stress?
The mineral will react to the stress, like, you know.
How will it react to the stress?
They will squish it. You know.
Squishing is one way it can happen, but how relative to the stress? Reorienting is one of the ways it can react, but how relative to the stress? Perpendicular to the stress, okay? So if I have a ball of Play-Doh right here and I squish it, I'm providing stress from this direction. In what direction is my Play-Doh going to squish? Up and down and out, perpendicular, 90 degrees to the stress applied. Same thing for minerals. They will reorient. They will recrystallize. They will squish, reorient, or any of those ways perpendicular to the direction of stress applied. Good. Foliation. Explain. I love it when I'm teaching my class and my arms are doing this and they're doing all crazy stuff and my watch tells me that, congratulations, you're exercising. Explain why clay minerals change into mica. It will change under pressure and temperature, but why? Yes. Does it have something to do with the minerals? I mean, yes, it has everything to do with the minerals, but what about the minerals? Not really that anything's being taken out. You can make micas entirely out of what is in the clays. There is probably going to be some desiccation going on. Okay, removal of water can definitely be part of this, or addition of water. But that's not what I'm looking for. Why would it change at all? Why does anything change? What's it in response to? Adapts. Hard to say that something like a mineral that isn't alive can adapt. So let's look for another way of expressing that same idea. Why does it change at all? The environment is doing what? Huh? It's changing. The environment is changing. And therefore, what is the mineral going to do? Change in response, because it is not.
Subject to the same.
It's not what? It's not the same environment, and therefore that mineral is no longer stable in that new environment. Clays not being stable in the new environment are going to change. And what are they going to change into under metamorphic conditions? Micas. Yep. When something in nature is no longer in an environment where it is stable, it will change. True of biology, true of geology, true of chemistry, true of physics, true of everything in science. Things in nature seek stability and will do whatever it takes to reach a stable state. Think of isotopes, right? Atoms that have gained or lost some mass in their nucleus, we call them unstable. And what are they going to do? They are going to blast particles off of themselves as radiation until they reach what? A new stable element. A totally different element, but one that is finally stable. Uranium-238, or 235, I should say, decays until finally it reaches stable lead-207. Yes. Yes, well, through a half-life, that's how we measure it. It takes a certain period of time for a certain quantity of this unstable isotope to reach that, yes. But eventually, it will reach that stable daughter isotope, okay? This is true of everything, okay? We won't go into philosophies of entropy here in my class. There are some who would argue against what I am telling you here, but it's simply based off of entropy, but we won't talk about that. All right, finally, distinguish between granite and gneiss. Oh, how do you distinguish between granite and gneiss? We also talked about this today as well. How do we distinguish between granite and gneiss? Granite is not foliated. Boom, there it is. That's it. Answered the question. Done. Granite will not be foliated. Gneiss will be foliated. It will have that banding, those linear, almost stacked minerals. Granite does not have that. Easy. Perfect. And I don't think I got any more questions from the online group, but let me just check. Nope. No more from the online crew. So let's come back to questions from you all. Let's see, we talked about half-lives and isotopes and such in lecture 1. So yes, that is included in lectures 1 through 7. What else? Did I show you all this ship that I made? I 3D printed this. If any of you have watched The Expanse on Amazon Prime, put that down. This is the Rocinante. I made it.
Rocinante?
Huh?
Is that what you said, Rocinante?
Rocinante. Yeah. It's like the main character's ship in the TV show.
Don Quixote.
Don
Yeah.
Quixote.
Yeah, it's the name of Don Quixote's horse. Yep. Yeah, it's got turrets that come out. The airlock opens. The landing gear moves down and up. It's pretty cool. I printed this in 128 pieces and then put it all together. It's kind of a hobby that I do. I have a 3D printer at home, so I print stuff like this and then sell it. So if you know any science fiction nerds that are interested in buying science fiction ships, let them know.
But you have to buy the things to make it.
The plastic, yeah. I get rolls of plastic and feed it into my printer, and then the printer makes the parts, and I put them together into that. Probably about $75 of plastic, plus the time and electricity that went into making it, plus the time that it took for me to put it together. I'll probably sell it for about $200. Yeah.
Gotta pay the bills, no?
Gotta pay the bills. Gotta pay them bills. Okay. What else? I haven't heard a question in a couple minutes. Are we drying up here?
I think that's all I had.
Okay. If you are in any way feeling right now like you are unprepared for this exam, now is the time to start getting prepared. The only way to feel prepared is to ask enough questions that you feel like you know what you need to.
The format was 40 questions?
40 questions, yes, sir.
Like 500 minutes, right?
500 minutes.
And that's when it's like due whenever that time runs out?
When that time runs out, it will auto-submit. If you close your window, it will auto-submit. If you refresh the page, if you lose your internet, you close your computer, it will auto-submit. There is no saving. As soon as you open it, that's your one attempt. You can only submit it. You cannot come back to it later. Unfortunately, if you decide to take it later tonight and you fall asleep before you finish it and it submits while you're asleep, I'm sorry. That's going to be your final submission.
Fall asleep.
That's happened. That happens to at least one person a semester.
It's gonna happen to you. Ian.
Each semester, at least one person will email me saying, hey, I'm so sorry. I fell asleep during the exam and it submitted. I only did 2 questions. Can you reopen it? I'm like, no. I'm sorry. You made the choice of when to take your exam and you put yourself in a situation for failure. I'm sorry. I gave you all the warnings in the world not to do that. I believe it's due on the 15th. So Sunday night. Okay. Sunday, 5 p.m., I believe. And that's just to make sure that they are all in so that on Monday I can have them graded so that on Tuesday when I meet with you all, hopefully you will have your final grades for those by then. Okay? And then we can start fresh with Module 2.
And don't start on the day it's due. Just
Yeah, do not start on the 15th if you can at all help it. Yes? When is the movie night? That is a good question. I still need to make that poll, don't I? Movie night poll. Movie night poll. That's really quick. Just look at a calendar.
I was thinking about the date thing though, because like when it's due is when it closes immediately, so you have the entire time to work on it. You know, if you start late.
That's true. That's a very good point. If you are planning on putting the exam off for a little bit, make sure that you start. If you want to use the maximum amount of time, bless you, you got to start at least 500 minutes before the due date, before the due time. If it's at 5 p.m. on Sunday, do the math and know you have to start 500 minutes before 5 p.m. Because at 5 p.m., Whether you've been working on it for a minute or an hour or 3 hours, it will submit. Okay? All right. I'm looking at probably October 4th or October 11th for our movie night. I think October 11th is the Friday before finals, right? Aren't finals on the 16th, if I'm not mistaken, 15th or 16th? It's that week. So it'll be the Friday 2 weeks before that or the Friday before that. So that's probably when I'll send out for the poll to have that. Actually, you know what? It'll probably just be the 4th. It'll just be on the 4th. I think that's easier. I think that works best for my schedule, and it's far enough in advance that y'all should make it. Yeah, so we'll just have it in that room over there so we don't have to deal with a projector that blinks out of existence all the time. Yeah, it's a little janky. You can bring snacks and drinks and all that stuff, songs. Huh? You can. I might. Depends on the day I might have had.
So can I pick a cake or
You can, yes, you can absolutely break a cake if you want.
man.
Oh,
Man,
this is
actually,
getting
no.
so special. I'm so excited. Huh? Okay. So, and if any of the online students this semester want to join us, please feel free. I will also be sending this poll out for you all later today. I'm gonna take care of this today. So on the poll, now that we know the day, the poll, it will just have what movie do we want to watch, and there will be a couple of different categories on there. I'm a big fan of disaster movies because it's in the disaster movies that they try putting all this science in to explain their logic for why all this is happening, and that's really fun for us to pull apart. Yeah. Sound good? Okay, and there will be an extra credit assignment associated with that I will give to you all probably that day. And you can work on it while we're watching the movie, or you can work on it after we watch the movie. For copyright reasons, I cannot broadcast the movie over Zoom or Collaborate or Class or any of that. I'd be in violation of film right copyright. If you have access to the movie, whatever it is, on your own, you can feel free to watch it on your own from home, or you could purchase or rent it however you want. That's entirely up to you, your own financial decisions. But I will be showing it in that classroom in 203, probably about 6 o'clock on the 4th. Let me write that down. 6 p.m. That's a Friday. 6 p.m. Goodfellas.
It's about fellas that are good.
Oh, is that what it's about? It's about fellas that are good. Yes, yes. I don't know what you take me for, but no. I'm a good fella, so you thought I'd like it. Hey, oh, hey. No. On the 4th. No. It's going to be a silly geology movie for a silly geology movie night. All right. What?
That's that one.
Oh, Journey to the Center of the Earth. Yes. Woo, feldspar. Yeah. Rubies, diamonds, emeralds, feldspar. Okay. Last chance to ask questions before I end the review and open the exam.
Can we help each other?
No, this is individual. No Googling. I should probably throw this out there. I have gotten very good at figuring out if an answer comes from Google. Let's see, how many is it now? I have thrown 2 students out of my class for cheating, and 1 person has been thrown out of the school because they cheated in my class and in another class. There is a 0 tolerance policy. The first time, you get a warning and you fail that exam. If it happens again in my class, I instantly report you to the college and you are failed my class, and the college can decide what to do with you from there. So please do not get tempted to use Google. I expressly forbid that. I let you use your notes, right? That should be enough if you've been paying attention. All right. All right. On that note, I'm going to end the recording and I will open the exam.